So thank you for joining us today, Professor Meyer. How are you doing?
I'm doing great. Thanks for inviting me.
Yep. And so I think one of the most interesting things is that you, in terms of being a Michigander, you're quite recent in Michigan. You've only been at the university for the past 3 or 4 years now. But before then, you've had a lot of experience elsewhere in the United States, as well as around the world, especially in Europe. So I was wondering if you could kind of bring us on that journey, starting from when you were a kid, what first got you interested in astronomy and research, and when everything kind of clicked as to seeing science as a viable path for your career.
Well, I think what got me hooked or ignited a spark was the PBS series Cosmos in the late 70s. I guess for me, it would have been early 80s. I don't remember exactly when the first airing of Cosmos was, but it was in popular culture and people were talking about it. And I saw it on our local PBS station and I was really obsessed with Cosmos. And so I subscribed to Astronomy magazine and I really thought space and astronomy and science was cool. I remember at the time, there was no internet. And so we had a World Book Encyclopedia, which was kind of our version of a hyperlinked text. And I remember I'd stay up late at night and I'd have like dozens of different copies. It went by letter. It started with A, B, C, and different volumes were the different letters of the alphabet. And so you'd read an article about space and then it would say at the bottom, see also, and then it would like drive you to new topics. And so I'd be flipping through on astronomy and then planets and this and that. And that was kind of like hyperlinking. So I remembered that experience of jumping around topic using the World Book Encyclopedia. Anyway, I then just always thought it would be so cool to be a scientist. And I have to say, I didn't read Astronomy magazine every month, even though I subscribed to it and I couldn't understand most of it. So then they would stack up and then I stopped getting it because this is a waste of money. So I had kind of a hard time engaging with local amateur groups that I thought were kind of sophisticated or sort of over my head. And it was sort of not fun sometimes. Or things got too technical. I had a hard time keeping the passion going. But when I always thought I wanted to go to university to study astronomy. And my family is not all of them, went to college, and my dad ended up going into the Army and worked nights and went to school during the day with 3 small children, blah, blah, blah. So it was a very different experience for me to think about going to college and studying something just for the sake of learning about it, as opposed to it being an absolute means to an end. My dad did get a college degree, but he himself was certainly a non-traditional student, and none of my grandparents went to high school. So I kind of don't come from a super well-educated family. So I didn't really understand where to go and think about, how would you study astronomy? That was so weird in my community. So I called up the local planetarium in St. Louis, Missouri. And the person is like, yeah, we're the planetarium. This is not the right place. But he got it. He understood what I was coming from as a junior in high school. And he directed me to a local university professor who was sort of, at the time, one of the only working astronomers in the state of Missouri. This would have been 83 or 84, I guess. And he gave me great advice. He said, if you really, 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 really know already that you want to do astronomy, you should go to some place that does astronomy. But, and he said I should look at the University of Arizona. And I had never really thought about something like that. But he also gave me even better advice. He said, but my recommendation is to study physics as an undergrad, and you can do that almost anywhere. And so that's what I kind of ended up doing. I went to college at Washington University in St. Louis, Missouri, and I was a physics major. And as I started learning a little bit more about science and getting more technical in my knowledge, I started thinking, oh, well, doing laboratory experiments and physics is really detailed and you can get real answers about atoms and molecules, and that's really precision science. And astronomy is so ridiculous, you can only learn anything to a factor of 10, And was that even science if you don't know the answer to better than a factor of 10? So I kind of got disillusioned with astronomy as a physics major. And then I had a good fortune to work. In fact, I can't even remember how I stumbled in to talk to this guy, but there was a person in the Earth and Planetary Science department, neighboring department, that needed a lab assistant. And so I started working with him one summer, and he was basically doing planetary astronomy, like looking at planets and imaging with CCD cameras that he built in his lab at telescopes in Hawaii. And I was like, wow, this is cool. So I really got the bug again working with him, and particularly got exposed to instrumentation and data taking and stuff like that. And that really kind of solidified my experience. I tried to apply to graduate schools. I also should mention that I had to interrupt my studies at WashU to take a leave of absence for 3 semesters for financial reasons. So I did 3 semesters at the University of Missouri, Columbia. And I think between it was the second semester of my sophomore year and my whole junior year. I think you could imagine that's somewhat disruptive for a curriculum. Right. So it was not a good idea to do that. And in retrospect, I might have fought harder to try to not do that, because I don't think that was super wise. Like if I had gone 2 years to someplace and then transferred, that would have been much better than like starting one place, going for a year and a half elsewhere, and then coming back and finishing as a senior. That was not a good idea. And I would not recommend that. But I also wasn't an A+ student just in general. I kind of had some holes in my background as a high school student, and didn't really, and then I was, not challenged that much in high school. And so I didn't really know how to study or have like a big goal that I needed to overcome and figure out how to be disciplined and do that. In my family, it was much more important to work outside the home. And so from 14 on, I always had a part-time job, mostly working in restaurants, first as a busboy and later as a waiter. And while it was great to have a lot of spending money, I didn't really apply myself in the right ways as a young person. That happened in college too. I worked a lot in restaurants. So anyway, I didn't get into graduate school when I was a senior. And so I had to kind of regroup there. And I decided to go to a local commuter university and offer myself as a graduate student there. I got a job as a teaching assistant. And I spent 2 more years going through their terminal master's program. So I took, 2 more years of courses. I then, in those days, of course, the physics GRE was a key part of your applications to graduate school. This was in 1989, 1991. And I really studied hard for the GRE, for that second ramp at grad school. I think I spent 6 months, and I did every single homework problem up in Halliday and Resnick, just all 30 chapters over and over again. And I basically doubled my score on the physics GRE. And of course, I had 2 more years of courses, and I got more exposure to research. And then there was an astronomer there. In fact, that one I had called as a high school student was still working there. And there was another astronomer then at that time. So I got into some research in infrared astronomy and star formation. And then coupling that with the laboratory work I had done kind of made a nice package for me. And it gave me a direction about where I wanted to go with this astronomy stuff. So the second time in 1991, when I applied to grad schools, I got into several different places, was able to go visit them and tour around. And it felt really good to be being recruited as opposed to being so totally shut down the 2 years earlier. Right. And in the end, I decided to go to the University of Massachusetts in Amherst, which had a very strong star and planet formation program and infrared instrumentation, which is what I wanted to do. And then after that, I had a little trouble getting on my first postdoc. I had a wonderful experience in Amherst, and I just learned a ton and really got confidence and got exposed to how to do research within a group and learn as part of a research community. And part of my research style I learned there, which was to kind of master the background information, the literature, and to be part of a community and to tell stories, to come up with hypotheses that kind of linked together the work that had been done in the past and try to spin that forward into new ways of thinking about the problem. And that research community plus the storytelling really inspired me to try to do my best in research. And that's sort of where I started to see more success. I barely got a job coming out of grad school, though. I didn't write enough research papers as a graduate student. And I actually got a job only because I had cold called someone in sending my CV to someone that I had met at a conference in Germany the year before, which I only went to. My research group couldn't afford to send me, so I paid for myself to go to this conference in Germany. And I met this person, and we hit it off, and they liked my research. And then he did not advertise a job the year I needed one, but I just sent him my CV and my application anyway, and he ended up hiring me. And that was the only job I got that year in 1995. And so I spent 2 years there. Then I was able to come back on a Hubble Fellowship, and I took it to the University of Arizona. So I finally heeded that advice I had gotten in high school at the Stewart Observatory. And I worked there for a couple of years and then was invited to join the faculty. Spent 8 or 9 years as an assistant and then associate professor there. And then in 2009, I moved to the Swiss Federal Institute of Science and Technology in Zurich, Switzerland. I had an opportunity to start a new research program there and a new group, and to join what was already an excellent exoplanet research community in Switzerland. And then partly for family reasons and other reasons, we decided we wanted to come back to the US. Both my wife and I have aging parents in the Midwest. I'm from St. Louis, and my in the out mid Missouri area, and my wife is from Chicago. And so we wanted to be closer to them, and University of Michigan was able to make an opportunity for us at the right time, and we're very, very grateful and have really enjoyed being here the last 3.5 years.
Professor Meyer, could we touch back on this problem, I think, in high school, that astronomy is one of the most captivating subjects, but a lot of people then go on to study physics or physics or just get turned off by science because they can't get involved, and it's quite hard to get involved in astronomy. But the cool thing is that now with the internet and all of these resources, people can get stuck in easier than they could before. Could you sort of describe for our audience a little bit some things that people could be doing in high school, or some interesting things that are out there that are perhaps not so well known, but that exist to get interested and keep the spark of astronomy alive?
Wow, citizen science is a new amazing frontier. There was even a story, I guess in January or February, of someone who had just joined a research outfit for NASA, and within a few days, as an intern, as an unpaid intern, and discovered an exoplanet from the test mission. Within like 2 days of starting on the job, working with folks at MIT. So citizen science is an amazing thing. I think you may have talked about this in your group before, that the Zooniverse is a wonderful gateway to many kinds of citizen science opportunities. And currently, there are opportunities for citizen scientists and high school students to go through test light curves by eye and look for unusual things. And it's not that we will mine the database visually with humans, for the next 5 years to find exoplanets. Right. TESS is a transiting exoplanet science mission that was launched by NASA 1.5 years ago and is doing wonderful work. But by inspecting and reporting unusual things, we are training neural networks and machine learning algorithms. So humans are still the best way to teach robots what to do. And there's just an absolute huge amount of work for people to do to really help in doing real science. I should also say that I'm part of the TESS follow-up network. We tend to do things like look for blended companions with adaptive optics at our Magellan telescopes, to which Michigan has unique access, or not unique, but preferred access. But many people who are amateur astronomers use small telescopes with CCD photometers and do photometry from their backyard. That is really vital to the whole TESS mission. So, and that's real data taking, where you upload the files and people do photometry, or astronomers at home do them themselves. And it's really a very, very important part of the mission. So there's something called the TESS Follow-Up Network, TFOP, and you can find links to that through the MIT website, the MIT Mission Control for TESS, TESS. So there's amazing ways. I should also say it's not uncommon for us here at Michigan to get requests for internships from just people who may even go to college elsewhere than Ann Arbor, but who live in the Southwest Michigan area in the summer, and then they volunteer for free to do research. And people, I would have never ever thought of doing that in the mid 1980s, but it's quite common now. And a lot of people even come to college with some kind of research exposure of one sort or another. So I think there are fabulous ways to get involved locally in whatever kind of community one is in. And of course, the internet has made all of this possible.
And I know you do offer the unique perspective, because you mentioned that there's a lot of local and national research that you were involved in and that people can get involved in, but you also had a lot of opportunities to do international research. So we're kind of wondering if you can explain and elaborate how research in the US compares and differs to research, say, in Germany or in Europe, and how different projects can be connected, or how those processes go.
Yeah, wow, that is a whole hour-long topic on its own. But let me say that it was very valuable for me as a postdoc to go and work for the Max Planck Institute for Astronomy, which is part of the Max Planck Society in Germany, and see that different way of doing research. In Germany then, and it's somewhat persisted now, there is a longer-term commitment to most of the funding lines that are available. So one of the things that is a hallmark of Central European science funding is consistency. There is a very steady growth with inflation, and budgets are flat but rock solid. You
Right.
would never experience a 20 or 30% budget cut due to an economic crisis. And I even lived through this in Switzerland during the Great Recession of the late zeros and into the early teens. We didn't even notice that there had been a financial crisis in terms of our research funding until about 5 years into it. And we got a little bitty dip, and then things came back up. In the US, for good and bad reasons, there is much more of a boom and bust cycle. So if you go back and look at the history of the National Science Foundation, even in the last 15, 20 years, you'll see campaigns or emphases that we want to double the biological science budget in the next 5 years or something like that. And so you'll see these huge ramp ups, and then things will flatten. And then in crises, you'll see things really cut. A lot of the discretionary spending in the federal budget can be very volatile, due in part to very reactive to the economic circumstances, which to some extent is reasonable, and also different priorities of different administrations. It's very, very difficult to plan out 10 and 20-year program budgets when you know that every 4 or 8 years you're going to be facing a very different set of priorities from different administrations. And you can see that perhaps all through your own lifetime. During President Bush in the zeros, there was talk of going back to the moon and Mars. And so things happened, and then they didn't happen, and then they happened again. So it's been a little bit this lurching. That can sound bad, but it's also true that kind of extraordinary increases can happen in remarkable times. And you can just say, yeah, we're going to do this. And 5 years later, it actually happens. So it's much harder in Europe to get like a gigantic project just launched off of the ground that would cost, $1 billion in the next decade. That just is not going to happen unless it's part of a 30-year-long plan. And to some extent, that's true in the US too. You can't just plop $10 billion down on something. But the US is more volatile in the plus and the minus direction. So it's easier to do more steady, longer-term things in Europe. I should also just say, though, that the whole university structure and the whole research institute structure is fundamentally different. The US, again, for good and bad reasons, can benefit from philanthropy. So people who have done very well in the private sector can become major sources of research funding. And this is something that really surprised me as I came back to the US in 2016. I've really been trying to tap into some of these philanthropic foundations to fund a lot of my research. And in Europe, that would be unheard of. You really wouldn't. The government is funding research enterprise, and you would not expect wealthy people. That is definitely something that the state is expected to do. I guess the other major difference is, of course, it is nation-state model, and there are continental entities, but these are member states that band together. For example, the European Space Agency,
Right.
which for good and bad reasons just operates very, very differently from NASA. And also each national science funding agency just operates on its own. And the federated European things are really only ESA and the European Southern Observatory, neither one of which is tied to a particular political union. So they are not part of the European Common Market. They are not part of the European Union. They are their own multinational legal entities that are not necessarily connected to politics or policy of different governments. So it creates pluses and minuses there too.
I think one interesting thing you mentioned, starting even in high school and early college, undergraduate years, is how your research goals and interests have kind of stayed the same over the course of your career, in terms of starting out thinking about instrumentation, thinking about stars, planet formation. And I'm curious to know how over the years your research has evolved and changed, and how maybe your outlook as to what you're interested has changed.
Yeah, so I think what I tell my mentees, people that I work with as undergrads and grad students and postdocs and such in my research group, is that the more you know about something, the more you're interested in it you tend to be. And so when I was first starting out, I'm not even sure how. I think I had to do a term paper on it. I got really interested in ultra high energy gamma rays. So these are very high energy radiation particles. They hit the atmosphere. They create secondary cascades of charged particles, which themselves create tertiary and fourth order cascades. And you see the showers come down, and then you try to pinpoint the source of the TeV gamma rays celestially, but you can only do so in the 80s, you could do that with an accuracy of several degrees. Now we've gotten a lot better, but I just thought that was super cool, like the highest energy radiation in the universe. And then I got interested in the lab I was working in spectral polarimetry. So spectral information, but also encoding the polarization vector of the light, and instrumentation that would allow you to do that. And then I started to try to merge the two, and I was interested in BL Lacerte objects, BL LAC jets, and I was going to try to study proton synchrotron emission in the infrared with the spectral polarimetry. And then I got exposed to infrared astronomy and star formation. So it just kind of started building on its own. I think the thing that I hit on that stuck was a bit combining the instrumentation with the infrared astronomy. And then the star and planet formation is a very obvious application of the convergence of those two interests in infrared and instrumentation. And then because of that, I chose to go to one of the leading groups at the time in star and planet formation at the University of Massachusetts in Amherst, the 5 college astronomy department. And there were, I think 6, maybe 7 different research groups all in that area. And then it's just popping. You know, I learned as much from the graduate students I went to school with as the half a dozen postdocs who were running around studying similar things, as the 4 or 5 professors who really ran the group. And then there was another research group in the interstellar medium, and that was where Professor Bergen was a graduate student. We were graduate students together at UMass. And so it was just a very rich environment and an exciting time in that field. And so when things are going well and they're interesting and you see a lot of energy and excitement around you and you're making progress and learning new things, you get more passionate about that topic and you learn more about it and you get more steeped into it. I guess for me, the big pivot, if you will, was when exoplanets were discovered. So the month I defended my thesis, the first detection of a gas giant planet around a normal star was made at a conference I was supposed to and give my thesis talk at, but I didn't go. I canceled the trip because I was just rushing around too much trying to finish. And at that meeting, they announced the discovery of the very first bona fide direct detection of a brown dwarf and an exoplanet in October of 1995. And then a paper came out in Nature in November, late November, early December, and it just exploded the field. I had been in a group studying the structure and evolution of circumstellar disks around young stars for many years by that point, but we always talked about planet formation, but we never really kind of jumped to say that we were looking for other solar systems, because we thought that would be too speculative or too flashy when you didn't have the data to back it up. But once exoplanets were discovered, then the whole field exploded. And those of us who were already kind of studying planet formation moved closer and closer to studying exoplanets. And a lot of other people jumped into the exoplanet game just in the observational side of detection and then later characterization. And it just led to a real renaissance in the field. And I guess now I describe myself more as someone who's studying the discovery and characterization of exoplanets than as someone who studies star and planet formation. But of course, I bring all that with me. And so I still occasionally do star formation related projects, and some students are interested in working on those kinds of projects. But I guess certainly in the last 15, 20 years, I have moved steadily and closer to exoplanets for sure. Because they're more, because of opportunity. You know, it's just, right. Wow, I can contribute here, and I move there. And that was a very natural evolution for me.
Mm-hmm. So you briefly described that that your role is in globally looking for and classifying and characterizing exoplanets. But could you go a little bit further into what it is that you're doing? What are the hypotheses that you're testing? Because I imagine that even before exoplanets were formally discovered, there was presumably an inkling that they would be out there, given that our solar system doesn't seem to be that unique, I would think. And so, but however, it must have seemed premature back then to just speculate about exoplanets and their science. But now that that is becoming a real, now that that's a mainstream scientific area, what are the sort of hypotheses that are being tested by scientists in that field?
So I'm glad you asked the question in that way, because that is the way I try to approach it. I still think of myself as an experimental physicist at heart. Mm-hmm. And I still remember, I ask my kids if they get this in school. We were taught a version of the scientific method every year in grade school, as far back as I can remember. And science doesn't really unfold that way, but there is a certain methodology of thinking about an hypothesis that can be ruled out. And this is something that I really try to emphasize to my students and other mentees, that if you're doing science, and I'm using that with a capital S, you would like a hypothesis whereby if you go looking for something and you don't find it, you can rule out a theory or some hypothesis on the basis of not finding what you're looking for. And that leads to good experimental design. And that means you can't lose. If I'm awarded 10 nights on an 8-meter telescope, I could find a planet and, wow, that's cool. And I'll publish that as a high profile detection. But if I don't see anything, the upper limit on their occurrence has got to be meaningful. So I've often been accused of kind of, making lemonade out of lemons. If I did this study or that study and I never find anything, I'm always spinning these little stories about how magnificent it was I didn't find anything. When of course, deep down inside, I was like, I totally want to see 10 planets, but I found zero. So to answer your question, what I am trying to do is to test quantitatively and confront theories of planet formation that should be predictive. They should have specific predictions that they can make, and then I look for what they predict, and then if I don't see it, I rule out that theory. And in particular, the way we talk about that is exoplanet demographics. I would like to know how common planets are as a function of the planet mass, maybe as a function of the planet radius, maybe as a function of the orbital distance from the planet to the star. And these distribution functions we call demographics. How common is a 1 Jupiter mass planet at 5 AU, a 1 Jupiter mass planet at 0.2 AU, a 1 Jupiter mass planet at 30 AU, around sun-like stars. And then I've kind of designed an experiment. That means I need different techniques to characterize the frequency of planets between, and I said 1 Jupiter mass, but now let me be quite clear. I need to measure it over a range, because I can't just have them be 1.000. That's too specific. So I say, I need to measure the frequency of planets between 0.3 and 3 Jupiter masses over a range from 0 to 0.5 AU, from 0.5 to 6, from 6 to 20, and from 20 to 1,000. So now I've separated 4 ranges of orbital distance, and now I've got a planet mass range, and each one of those ranges might require a different technique to find the planets. And I want to go as sensitive as I can and be as successful as I can. But more importantly, I need to know the limits of each survey that I would design, what sample size I need. If I'm going to look at 3 stars and I find nothing, well, that's kind of maybe not a very robust result. If I look at 130 stars and find nothing, you can think of Poisson statistics on a probability of success going as the square root of the number of experiments you try. So 130 is getting up there. So that's a good sample. And therefore, we try to learn how common planets of a different type are. And then if I do that whole thing, I repeat that experiment for stars that are much higher mass than the sun, what I would call intermediate mass stars, say 1.5 times the mass of the sun up to say 3 times the mass of the sun. And then I repeat that experiment again for low mass stars. And there, I'm kind of doing a planet formation experiment. And the big knob that I'm twisting is stellar mass, which I think gives us a big handle on planet formation around stars of different type. And ultimately, I would like to be able to predict how common planets of a given size and orbital separation are around all types of stars, even ones that I can't observe in galaxies that are 1 million light years away, going back maybe to the early universe. And yes, eventually, if we want to use these kinds of observational programs to constrain the frequency of rocky planets that might be in the liquid water zone of their host stars, and ultimately, we would like to place constraints on the probability of biochemical origin of life in the universe.
Before we get there, though, presumably there's a massive work. There's going to be massive work in improving our methods of detection, our observational methods, our statistical methods, our computational methods. And I know that, and you briefly mentioned that you were interested in instrumentation. Could you kind of explain how the field of instrumentation, and this particularly the part that you're involved in, has evolved with the advent of the computer technological era? Because I think, at least from our perspective as students, computers have enabled a lot of things to come down and to be far more accessible by everyone. But on the other hand, I assume that computers have also enabled the upper ends of science to progress faster and better than they would have before. So could you kind of explain your role in instrumentation and all of that kind of stuff?
Okay, so instrumentation, when I started graduate school, and maybe it was even unique for that time, but I had one of my supervisors was very much a tabletop experiment person. I don't consider myself an instrumentalist in the way that I consider Professor Meyer, John Meyer in our department, one of these world-leading experts in his specific technique. And my old supervisor was like that. I joke that he could go into a garage, basically all by himself, and come out with like an astronomical instrument, because he could do the wiring, he could do the electronics, he could do the optics, he could do the computer programming. I mean, he could do everything. I'm not like that. I'm much more of a tinkerer. I like to come in and recognize a new application or an augmentation to some other existing technology or instrument that can enhance. And the reason I'm really passionate about that is because I really want my field to make rapid progress towards the answers that I am just, I mean, the thing that drives me is I just want to know the answer. I just can't stand not knowing the answer. And so if I can help make a little widget that will get us closer to the answer faster. I also tell people that at heart, I'm just basically lazy. So if you told me I had to take a little pebble and like push it up with my nose up a mountain for like 10 years, or, you know, you could go into this laboratory and make this pebble nose pushing widget and it could happen in like a week. I'm like, I'm totally going to go do that, you know, because I can't wait. I'm impatient. So, okay, so instrumentation, when I started, my professor was really good at just enabling us to, here's a detector, here's a 0.4 meter telescope, design a spectrograph for it. Okay, so then you scratch your head and I'd open a bunch of textbooks. And this is, again, a thing where I learn by doing. So in the last 20 years, a lot of our educational innovations have come from recognizing that inquiry-based discovery is an important tool for you to absorb deeply in your intuition, physical intuition, and your worldview, concepts of physics and math that you're learning at a lecture in a classroom. And that was very natural to me because I did most of my learning arguing with my fellow students in a late night laboratory study session, or in a laboratory actually building things with my hands. That's where I really got it. So those things resonate with me, which is why I love teaching Astronomy 361 so much in our department. Right. So in the early days, it was much easier for instrumentalists to build their own things. They didn't need that much money. Even back then, it was a lot of money, but $100,000, you could kind of build a camera for that in the 80s and 90s. Nowadays, as we get up to 8-meter telescopes, 6.5-meter telescopes, the instrument budgets are millions. I just had a grant approved of order that to build a new camera for Magellan. And then if things start getting that expensive, and space is even a whole nother thing. I mean, the instrument budget roughly for the near-infrared camera for the James Webb Space Telescope is about $130 million. So what does that mean? That means I'm not going to be able to take a first-year graduate student and just throw them into the lab with a screwdriver and a hammer and say, yeah, go adjust that thing, you know, because all of a sudden, you know, they put the screwdriver through the detector and $130 million goes away. So as things got more complicated, number one, you could not be a master of everything. It's just impossible. And things got so expensive that the nervousness and the professionalism and the management of having to navigate a project that complicated and expensive made it less accessible for students to get their hands dirty in the lab with a project. So that's unfortunate. Big, expensive projects also take a very long time. So one example I think you might be interested to hear about is the camera for the James Webb Space Telescope. I started going to meetings and serving on a committee to design, or at least discuss the attributes of instruments for that telescope in 1997. And we finally wrote a proposal. I was part of 2 proposal teams to build, or ended up being part of 2 instrument teams. In 2003, I think, we were awarded the contract. And so it takes 10, 15, 20 years to build an instrument that complicated. And frankly, the near-infrared camera, NIRCam, which is being led by the University of Arizona by my wonderful colleague, Marcia Ricci. She is she's like John Monnier. She's one of these, you know, real world leaders in her field. And we hosted her for the Muller Prize right before the shutdown here at U of M. She's fantastic, and she led that whole project. She almost did it all by herself, but she worked with industrial partners. So we worked with Lockheed Martin. And it certainly wasn't the case that we got to go into the lab and play with little bits of that instrument. But I was there as a kind of an advisor for much of the science that we wanted to do and the scientific requirements that the instrument had to make in order to fulfill its promise and its dream. And that project took a very long time, and a project like James Webb in particular was unique. You know, this is a proper use of that word. I think the astronomy community has certainly never had a segmented telescope that needed to deploy on orbit, where astronauts were not going to come like Hubble and revive it or refresh it occasionally, and at a level of tolerances that were really unknown. People often ask about the cost overruns for James Webb. And while they're challenging, and certainly one can point to mistakes that were made along the way, it is very difficult to know exactly how much something will cost that's never, ever been built before. And whenever you face a challenge that you need to fix or a problem, I have tremendous admiration for the engineers and technicians who overcame all of those hurdles over the last 20 years. But it is an expensive proposition, there's no doubt about it. I can also say that sometimes the uncertainty of funding, or the unknown contributions of partner countries, or the management and the way such a complex international project gets brought together adds additional cost that doesn't necessarily buy value. But, you know, if someone came to the right group at the beginning and said, we'll give you exactly the amount of money you need for it, You don't need to have reviews. You don't have to do any bureaucracy. You should do reviews that you think you need to do technically, et cetera, et cetera. I don't know how much the telescope would have really cost if it had been done perfectly. But the chances are it wouldn't have been done perfectly because it had never been done before. And it's just very hard to value. But I think it has taught us that as we got to these bigger and bigger things, and of course the space game is very different, but we're getting there with ground-based instrumentation too. There's a level of professionalism and a level of redundancy and a level of design checking and rechecking and triple checking and management of thousands of people who cannot be co-located, and how you design interfaces and manage the design of those interfaces. All of that sort of may sound boring as like management 101, but it gets to be hugely important to the successful completion of a project that's of the billion-dollar scale or that's going to last over decades, which can be more than the professional lifetime of people who come and work on a project and move elsewhere. So I have to say, as things have gotten more complicated, it's gotten harder to involve students in the nitty-gritty and to connect the dots between the technical knowledge you need, between the physics, basic research you need, between the computer simulation you need, the software development you need, etc. I'm sorry, I'm answering a very expansive question, but I think you also asked about computers and their role in this process. That is multifaceted. I would say I still gravitate towards new instruments where the basic physics technology itself can create an order of magnitude improvement. And that's generally not going to be the case for a computer. A computer is going to help me extract very efficiently the absolute amount of information that's really contained in those images, and my ability to do Bayesian analysis and to use proper statistical inference, which I have to tell you has grown by orders of magnitude since I started as a student. I published papers doing things 20 years ago that I would never be allowed to do today.
Right.
One of our astronomy representatives for the Michigan Data Science Institute, Chris Miller, is a real expert in some of these statistical techniques. And Oleg teaches a course in computational astrophysics using techniques that I could have only dreamed about in the early 90s. But now, yes, you have to use this kind of state-of-the-art approach to extracting information. And I guess my feeling is that software development has saved us orders of magnitude in time, just absolutely in time. Techniques have saved us factors of 2 and 3 in our ability to really pull things out. You know, you can't make a source appear in the detector if it's not there, but computers can help you very accurately know what your real errors are. And that is a huge boost to the field in terms of doing better science and hypothesis testing. But there is still a role for a new solid state material that can detect photons at a rate 2 or 3 times more efficiently than another one. And because the observations tend to go as the square of the signal to noise goes as the square of the exposure time, if I can improve things by a factor of 3, that turns into an order of magnitude savings on the telescope time. And that's a big, big deal. And I get very, very excited about helping make those leaps go forward.
So compared to before, when we were talking about citizen science and people using this transit method where they can see the light curves on the internet and kind of locate where those are as the exoplanet passes in front of the host star, what other techniques do scientists like yourself or other astronomers use to detect these exoplanets? And like, to what accuracy can we detect these wobbles? And what's the future of exoplanet discovery and studying their atmospheres?
So the first thing was radial velocity. That was the first discovery in 1995. And that was done with a spectrograph that had an accuracy of a few meters per second, whereas 1 meter per second is about human walking speed. That's about how fast we can measure with our Doppler radar gun the speed of a star as it is moving in response to the dance of the orbit of the 2 bodies around their common center of mass. So as the planet moves one way, the star is moving another. So we're indirectly detecting a planet using radial velocity, like your Doppler radar gun if you get a speeding ticket on a highway. The transit technique, as you mentioned, is the diminution of the light as the planet goes in front of the star. And that to detect an Earth-like planet around a sun-like star, you would need a spectrograph with a spectral resolving power for radial velocity that was about 10 centimeters per second. So a full order of magnitude better than human walking speed. The transit technique to detect the shadow of an Earth passing in front of the surface of a sun, you need about 10 or 20 parts per million in the accuracy of the photometry. So you're measuring brightness changes at about 10 parts per million. That is really hard. It's practically impossible to do from the ground, which is why space-based observatories like Kepler, like the TESS mission, and like the recently launched Swiss CHEOPS mission are done in space without the corrupting effects of the Earth's atmosphere, and other special techniques to get around weather and clouds and things to do precision photometry. So hopefully, starting now and going forward, we'll have the accuracy to measure the radial velocity shift of Earth-like planets around sun-like stars, but then we need to wait for the orbits. So an Earth-like planet at 1 AU takes a year to go around its star, and you probably want at least a few orbits before you can say you've confidently detected something. So the technology is there sort of starting now, and going forward around bright stars, we should be able to start seeing those discoveries accelerate again. The transit stuff is just going wild with the space-based observatories and ground-based complementary ones too. I do direct imaging. And this again comes from my heritage or my background in infrared astronomy and studying star and planet formation. In the mid to late 90s, we were pushing to find brown dwarfs in star forming regions. These are objects below the minimum mass where eventually a star can fuse hydrogen into helium in its core and have its own nuclear furnace, an energy producing source so that it can shine. Brown dwarfs are stars that are too small of a mass so that they can't convert enough potential energy into internal energy in their core to get the temperature high enough to sort of kickstart those nuclear reactions going. And that has to do with nuclear physics and the gamma curve and so on. But to try to keep me on track here, we were looking for brown dwarfs and say maybe trying to find a 10 million year old 30 Jupiter mass brown dwarf in star forming regions. The technology to do that is not so different from trying to take an image of a 1 Jupiter mass planet closer to its host star. So I was kind of on that track, and it was an easy pivot for me. What has revolutionized the ability to do direct imaging, which is looking at faint things near bright things, is adaptive optics. This is the ability to take out wavefront errors that are introduced by the Earth's atmosphere and try to get back those perfect plane parallel waves of wavefront from our star and planet, and do that by modulating the optics in our system so that we can reach the ultimate diffraction limit of a telescope, the so-called Rayleigh limit, which is proportional to the wavelength of light you're observing divided by the diameter of the telescope, lambda over d, as we call it. And the ability to do that can get you, for an 8-meter telescope around typical nearby stars that are young enough that we could still see planets from the glow of their gravitational contraction, we can probably do that around at about 30 AU, maybe 20 AU, maybe 10 AU for the very nearest systems. The nearer by my targets are to my telescope, the better the physical resolution is of how fine I can resolve things. Now, if I told you I could see a Jupiter mass planet at 20 times an AU, which is the mean distance between the Earth and the Sun, I wouldn't see Jupiter that way. Our Jupiter is at about 5 AU, 5 times the mean Earth-Sun distance. So if there was a Jupiter mass planet at about 20 AU around a star at 50 parsecs at about 30 million years, I could see it. I could take a picture of that thing. So what we're doing is designing experiments using state-of-the-art adaptive optics on the world's largest telescopes to try to resolve Jupiter mass planets around sun-like stars. And so far, we've detected about a dozen of them. And that's not as many as the 3,000 plus, 4,000 plus planets that have been discovered from transit. So we're kind of the poor relations here. We have not detected so many objects. But what we are useful in doing is placing upper limits or measurements of the occurrence rate of planets at large orbital separations.
Mhm.
And what we have found in those kinds of studies is that planets that are really, really, so if, imagine that the star is here on my left hand, planets that are really close to the sun are there, but not so common. And as I get out to distances of 2, 3, and 4 AU, that seems to be about the peak in the orbital distribution. And then we start to see it falling off again, which is bad for me because I don't get to detect a lot of planets. But we design our experiments to measure that distribution. And just in the last 2 years, we've been able to point out that the peak in the distribution of gas giants around sun-like stars, M dwarfs, and I'm starting to also believe intermediate mass stars, is all about 3 times the mean Earth-Sun distance. And that's kind of a new discovery of a new fact about the distributions of exoplanets, which we couldn't have done without direct imaging. More fun is to detect something. And if we detect something, we can take spectra of those planets and analyze their atmospheres. That allows us to guess the temperature. That allows us to look for the atomic and molecular fingerprints of different species in the spectra of those bodies, and then look at their composition to learn how much carbon, nitrogen, and oxygen they have in their atmospheres. And that is another handle. The gross demographics also should be a predictive outcome of planet formation theory, but also what planets are made of is a powerful constraint on planet formation theory. And ultimately, I just really want to know how planets are formed. How common are they of different types? And again, ultimately, we'd like to know how common potentially habitable worlds are elsewhere in the universe.
Mm-hmm. And I know you mentioned earlier that there is a lot that goes into funding different projects. One of the things that we found was the Decadal survey. So essentially, it's kind of a committee that overviews and distributes a lot of the funds that's like overlooked by NASA and the National Academy of Sciences. So how does organizations that distribute funds like the Decadal survey impact the research that you're doing, and how can it change the field of astronomy, and what's more prevalent and what's not?
So let me clarify. The National Academy runs the Decadal survey, and this is requested by Congress, and the document that is produced in the end goes to both NASA and NSF. It is a plan. It is a recommendation. It does not give out funding, but it tries to set priorities from the community. And generally, the administrations that execute, and the Congress that appropriates the money, and the executive that tries to execute the appropriations, tries to listen to the recommendations of the Decadal survey. And that's a tradition that goes back to the 1960s. Astronomy did its first Decadal survey back then. I think we're on our 7th now that we're doing now. We tend to do them every 10 years. I think the first one was called the Field Report from George Field, who led it. And this wasn't generally done by other disciplines at the time. And by the 80s, 90s, and zeros, other disciplines got online and decided that this was actually a really good idea to let the community kind of bubble up its own plan, give it to the government, and then hopefully the government would execute the most important parts of it. The government can and does sometimes disagree with the survey. They try not to, but there can be reasons down the line where they are unable to, for whatever reason, maybe they don't have enough money or whatnot, so they need some guidance, but they can't always follow it to the letter. I'll also just point out 2 things. Our whole national science funding infrastructure only arose out of the ashes of World War II. And there really wasn't a thing like government-funded research before World War II. People saw the value of it in trying to bring the economy of the world back. And obviously, there were researches that were related to defense that became part of that research complex as well. The other key thing that was before your lifetime was the Apollo program, and before mine too. I was barely alive when people landed on the moon. But the extraordinary amount of science funding that started really our space program in the 60s is unparalleled. And if you extrapolated the rate of growth of science funding from the 1960s forward to today, we would totally have to be mining asteroids to have any sort of productivity to fund a research enterprise like that. I mean, it was just off the charts. So it had to flatten out. And what I try to remind people as we go through each decadal survey is there really is no normal of science funding. We're all just sort of figuring this out in the last 70, 80 years. And different cultures and societies will place different priorities on different things. And that's reasonable and right and good that they do that. And we, as scientists, will have things we want to do, and we think they're aspirational, and we think that they can inspire. We think that they can help attract people to science and education, which is healthy for all of us. And they might even have unintended practical benefits down the road, which we all benefit from, which we can come back to in a minute. But the survey, as it is constructed by a plan that NASA makes with the NSF and DOE and other funding agencies, and they collaborate with the National Academy of Sciences, which is this select group of self-selecting people, which is dominated by the older, more accomplished, more senior members of the community, which, by the way, is not the most diverse and most representative body in the field. And they get together and make a plan for the survey. They pick chairs of the survey, and then the survey chairs get to then pick their central committee that's going to help them execute the survey. And then there's several subcommittees that are formed on different science areas or on different wavelength regimes or different techniques. And all of these subpanels are then populated. Reports are received. There's a call that goes out for white papers. This is a funny term, and I had looked up the origin of it, why they're called white papers. And I can't remember the answer off the top of my head, but I think it's on Wikipedia. And people write these kind of policy documents. I study exoplanets, and so we want to explain to the decadal survey how important it is to study demographics, as I was explaining before, the distribution functions of these planet populations. And so we write a paper about how important that is for all of science and for exoplanets in particular, and what capabilities and facilities we need to make major progress. And we're given rules, like the paper has to be due on 2019, August 3rd, and it can't be more than 12 pages long, and it has to be in this format. And so hundreds and hundreds of these white papers are written, and they go to these panels, and they're read. And then the panels can invite different groups in to pitch ideas or to propose projects. And then each of those subpanels writes a sub-report, which then goes to the central committee. And it's a huge, huge effort. It involves dozens to hundreds of people, and literally tens of thousands of members of the community involved in writing white papers and different things. Town halls are held at the American Astronomical Society meetings, which are not happening face-to-face now, but certainly happened in January in Hawaii. And so they try to keep people informed. They try to gather feedback on process. There are panels about the state of the profession, so that people have an opportunity to complain about the unhealthy elements in our profession, how they feel like it doesn't really promote healthy work lives or family-friendly work environments, or that makes it difficult for underrepresented populations to really get into the field and fully contribute in the most important way. So there are lots of voices that come into the decadal survey, but ultimately it comes down to sort of one 150-page report, which has a series of recommendations, and they can't touch on everything, and they certainly can't get everything right. They also have independent costing estimates for all major projects, because they don't want to, suppose you had $1 trillion astronomy budget for the next decade. Well, you can do everything. You don't have to make tough choices. But what the charge to the survey is generally to rank order things, and not to say, have to fund this, don't fund that. They're really just meant to prioritize things, because we don't really know how the budgets are going to go down the road.
Right. And then so once things are prioritized, obviously, a lot of astronomers are going to need to go to like observatory facilities and schedule telescope times. I know the University of Michigan offers a spring course that allows us to go to Kitt Peak National Observatory and have some time with the telescopes there. But would you care to go into the logistics of how, without those kind of special opportunities, how most researchers apply for telescope time, and how all of those processes work to actually get the data?
Sure. And I can say that it's true for getting funding for research. It's true for proposing new instrumentation, and it's true for getting telescope time. is that these are all oversubscribed quantities by factors of a few to factors of a dozen or more, 12 to 1, 20 to 1 chance. So we write proposals. And again, we're given guidelines. You need to address these elements to it. You need to show how your work or your observing can really make an impact in the field. And then we submit these proposals, and then there's a committee that's chosen, which rotates every year. It can be slightly different, that evaluates these proposals and tries to assign time on the basis of the technical feasibility of the program, the quality of the science, the confidence that the research can get done, and the impact that that research would make on all of astronomy. And so a working professional astronomer has to get good at writing proposals. Otherwise, you can't get telescope time, you cannot get computational time on supercomputers, and you cannot get research funding to do the work that you want to do. So it's peer-reviewed, competitive proposals. They're generally anonymous reviews. We are now moving to a place in our field where double blind is more common, where not even my identity as a proposer is revealed. With all academic pursuits, I think there is a tendency towards conservatism and playing it safe and going with what you know. And in fields where there are large, important, underrepresented populations, those mechanisms can tend to make the rich richer and the poor poorer. And so if there's some 60-year-old guy who just has always gotten 10-meter telescope time and just keeps getting it, that makes it easier for them to write better proposals. And then that person's name, and you think, oh, wow, so-and-so is really a great astrophysicist and will do a great job. And so I'm just going to give the time to them, and I won't even read their proposal that carefully. Well, it's really hard for a younger person or women or people of color to participate and to compete equally on a playing field like that. So one thing the Hubble Space Telescope pioneered in their proposal allocation was to make it blind, so that you would not know who I was if I was proposing to you. And it's a double blind. I don't know who the reviewers are. They don't know who the proposers are until after the grading is done. And we saw in a few experiments with this that actually made the successful proposal group much more diverse than the previous versions. And so this is now getting to be a norm in the field. More and more competitive things are moving towards that double-blind procedure. So that's a really positive element.
And now with COVID-19 and this disruption it's caused not only on astronomy, but science in general, how does this change the proposal process, and how does this change going forward after the Decadal survey and our outlook in astronomy? That we're kind of delayed. Are people who have telescope time reserved for the next few months told no, they can't get it and they have to reapply next year? Does this make it more competitive in the upcoming years? And have you directly been affected in terms of getting telescope time?
Well, as with everything, we are all affected. Our observatories have been shut down for months, all of them, all over the world. The Michigan access to things at Kitt Peak is shut down. The Michigan part of access to the Magellan Observatory has been shut down. The European Southern Observatory has been shut down. Everybody's shut down. We still don't, I had telescope time. We had 2 observing runs planned for April and May. They were both basically canceled. I might find out today that one of my graduate students still gets a little bit of time in late May or June, not even on the instrument he wanted to use. So it's kind of like a total backup project. So everything is just completely chaos and unprecedented shutdown right now.
Right.
So sort of as they reopen the observatories in the next few months, kind of random things will be getting done because none of the instruments that were planned are on the telescope. And so you're really playing catch up. We're in the process of reviewing proposals for the next term in the fall and winter. We hope things will be back to normal at the observatory. We have confidence, and it's reasonable to expect that they might be and will remain that way for a while. So I think going forward, at least the telescope time access will come back to normal. It might be much more common to do service observing or to send one group of people to do observing for a large number of different programs. Astronomers, particularly at Magellan, it's a little bit old-fashioned, and people like to go down there and take their data themselves. And I'm among them. I would love to be there and do it, but I also recognize that it's much more cost-effective than to fly all these people all around. And sometimes even a technician who's not the expert on the observing program knows how the instrument works better than the random person from one of the 8 institutions that wants to go down there. So there are good reasons why service observing or queue scheduling or remote observing are better. Anyway, so we'll get back to normal on that front. Right now, all proposal reviews that are in process for funding for the next years are being done remotely. That's different than having a panel meet face-to-face, but I don't think fundamentally so. So I think what we'll even find in the next several years is that we'll probably be doing a lot less professional travel. Not just even so much because it's so dangerous, but because it's just really not necessary. Right. There is value added to being in person, but it's maybe a 10 or 20% value. And the extra cost, and frankly, I've been worried about this the last couple of years, even though I haven't really curtailed my professional travel. It's one of the worst things that I personally do to the environment is to fly in an airplane. Right. Compared to my recycling, milk canisters and things like that. Me taking, 20 flights per year internationally, that's really terrible for the environment. And so I should think more broadly about my impact of my work life. And I think we have realized, even though these Zoom and Blue Jeans and video conferencing are not ideal, they are good enough to save some of the work travel. So we'll probably be decreasing that. As far as the future of the execution of the decadal survey and what's going to happen, honestly, we don't know. I think none of us know what's going to happen to the economy and how government funding will be affected. My own personal experience when I was in Arizona and transitioning to Switzerland during the Great Recession between 28 and 2010, it was very dramatic. The University of Arizona suffered a lot during that economic crisis. I think Michigan is probably in a somewhat better quote a business model or financial model to most state universities, so they will do better than most. But we have taken a very, very serious hit. I think it's really, really hard to say. None of us know how this is going to affect the economy in the long term. And something else I tell my students and postdocs that you haven't lived through yet, but in my professional life, when I started applying for grad schools in 1991, we were in the middle of a recession. And one of my advisors told me I absolutely should not go into astronomy. It's just so terrible, and through financial crisis, nothing will get funded, and you're really taking a risk you can't justify. Things will go up and they will come down at frequencies and durations that is very difficult to predict over your professional life. So I also have to say, I think we are facing a new reality in terms of priorities for our culture and our society and us personally. And so who knows what the future is going to look like. I think there will be efforts made to stimulate the economy, the good efforts made with good intention. I think in some cases, the work that we do in astrophysics intersects with certain industries like aerospace industry and space industry. And some of those injections of funds will mean that it's easier maybe even to get certain kinds of projects going related to the aerospace and space industries and other kinds of technology programs that do interface with astronomy and astrophysics. So those might benefit, surprisingly, or in the near to midterm, and other things will probably get delayed. One of the projects that's on the horizon for many of us in astronomy are the ground-based construction of extremely large telescopes with diameters between 25 and 39 meters, which are really the future of ground-based astronomy. We expect delays, but we don't expect that those are going to go belly up. We're very excited about those capabilities in the future, but there will need to be a balance between what we need to do as a society and as a population, as humanity, to make sure that we take care of each other during this time.
Yeah, and I know all of these stay-at-home orders are really bringing an emphasis on a lot of medical research, and that people are going to want a lot of funding into cures and disease prevention. So I guess a thought in the back of people's minds would be then, how would astronomy then affect the medical and disease prevention, and also affect the big vision that we're seeing on climate change? How would astronomy change how we understand our own planet's climate now that everyone has been staying inside, and we can see that there's been a lot of improvements, like dolphins returning to Venice and different things as such. I guess a lot of people will be questioning why we would keep putting money into astronomy, considering that one disease could cause this much chaos and that we should probably put more money into medicine.
Well, I have to say I can't deny that I wish we were funding our biomedical research infrastructure at a higher level right now. Yeah. And if we're going to talk about Apollo programs, boy, I'd sure like to see an Apollo era investment in vaccines for COVID-19.
Right, but I know you mentioned like studying different planets could help us understand our own. So
yeah, well, and even beyond that, I think, and I'll come to that in a second, I think the detector technologies that we work with can have biomedical applications. Mm-hmm. And related to that, the software development and the algorithm development that we do for image processing turns out to be a huge part of magnetic resonance imaging and looking for tumors in people's brains and things like that. So there's a lot of overlap between medical imaging and astronomical image processing that's extremely practical. Mm-hmm. Not to mention the energy in big data and machine learning, that where astronomy is really at the forefront. I think there will be a lot of unintended benefits from the kinds of research that we're doing. I tried to mention before, there is a lot of real interest in keeping some of our big manufacturing and high-tech industries going, and that will be part of it too. But I also do believe that the kinds of work that we're doing in the most basic astronomy research, such as searching for, finding, and characterizing exoplanets, could have long-term benefits. And one of the things that I like to emphasize is that atmospheric chemistry and the diversity of planetary atmospheres is bewildering. We see iron sulfide clouds and rainout on exoplanet atmospheres. Mm-hmm. We find variations in the carbon to nitrogen to oxygen ratio that we couldn't fathom before. And I think what we'll find in the next 10 to 15 years, even if we try to look for life and don't find it, I think we will find a diversity of complicated exoplanet atmospheres, which will hopefully, there will be some understanding of the patterns in those data, which I akin to understanding climate as opposed to studying the weather, which is sort of chaotic and complicated. And if we can find patterns emerging in atmospheres of other worlds in very extreme end member cases of the kinds of atmospheric physics we study, maybe we'll even find some unique insights into how our own planet and atmosphere has evolved and what we can do to help it heal itself over time.
So, Professor Meyer, you mentioned that that we can learn things from other planets. I guess where I'm going with that is, it might seem a little bit fantastical to many people to think that a planet where there's iron clouds and things like that. I think it might seem a bit fantastical to some people, and it doesn't really seem like there could be an earthly application to just knowing the fact that there are things like that exist out there. So, for example, how would knowing something like that help, everyone, the global community, deal with the problem of climate change that we have now?
I'm not an expert in atmospheric chemistry and dynamics, so I can only outline in broad brush what I'm trying to get at. But suppose that under very specific temperature and pressure conditions and at certain concentrations of certain kinds of chemicals, a new series of chemical reactions is initiated, and the agent that ultimately changes the composition of the atmosphere does not immediately present itself until 3 steps into the chain of those reactions. Maybe such a process could be even discovered and understood in an incredible, weird alien world atmosphere. But the idea of discovering that process, which we might then call the Ann Arbor process, is discovered. And that same kind of process could be realized under incredibly different temperatures and pressures and with different molar concentrations of other species. But the process itself could still happen in a different context that might lead to real changes in a more Earth analog atmosphere. You can imagine connections like that being made. and that the simple, we can't create everything in our laboratories. And so going out into the universe and finding extrema is sometimes a really good way of learning what's possible, which we can then adapt and change to understand things that are more terrestrial to us.
Cool. Thank you.
Yeah, but unfortunately, COVID-19 has kind of locked us all inside, and those wonderful discoveries, like you mentioned, have all been put on hold. So in the meantime, I know a lot of people have been turning to the fantastical, especially with this video of a supposed UFO that the Pentagon has released. We know that you haven't seen it yet, so I'm going to pull it up for you, and then we'd like to get your thoughts and kind of your first initial reaction to what this may be, if you think life could become this intelligent without us knowing, and the things that a lot of science fiction is based off of. I'll get this here for you.
Yeah, and I guess just to narrate over to the people who are listening to this instead of viewing the actual video, we're just viewing a Pentagon video that was released in mid to late April, I believe, from I think 2005. One of the videos was, and then also the other one was, two of them were from 2014 or 2015, and it just depicts your usual, UFO video, some unidentified object flying over water or land.
Yeah, so I believe this was some Navy training exercises, and then they picked up on these different objects that they have confirmed that they still don't know what they are.
Okay, so it looks like a potato. I don't know how big it is. Is it
Right?
Is there a scale? Do they report a scale anywhere on how big it is?
They did not, but they did report that it was flying at around Mach 0.55.
Yeah,
which
it looks like 120 knots is the wind, and then it's keeping up with them at supersonic speeds in their jets.
And I think one of the fantastic things with this video that's come out is that, and I mean, this has gone around, but I've heard so many people talk about this, even in my friends, my family, the internet. I've seen this video a little bit everywhere, and I think what's quite amazing is that when we consider how large space is, and that we've never really even come close to finding anything scientific, anything rigorous about aliens, there's been, and I think this might be throughout time, we've had all of these little inklings that this could be something that is perhaps cannot be explained by our earthly means yet. And so we turn to just speculating that it's just aliens out there doing this. But I mean, I think this, and that to me is more in the realm. And I mean, we talked with you earlier on, and you talked about this too, how this is just more exploration and potentially even wild speculation than rigorous science. But I think it does captivate the imagination. And I was wondering what your thoughts were on these kind of things. We have gotten signals from outer space that cannot really be explained, like the WOW signal. We now have these videos. I know there's other little things that exist out there that cannot really be explained. So what are your thoughts on that as a person who is doing a science so closely related to potentially astrobiology? What are your thoughts on aliens, if we can put it like that?
So I am not impressed with that video. I mean, I would love, when I was a kid, after I saw the first Star Wars movie, I just dreamed every night that somebody would just swoop down and pick me up off of my, dead end street and take me up into the stars. So I get it. I would love to meet aliens. Although now that I'm 53 and have kids, I would be super terrified of,
Right.
if that's an alien. I mean, I'm going to go off the grid or something. There are so many other ways to explain everything that I have seen, including the WOW signal. For those of you who want to research it in the radio astronomy literature, it is curious. but there are still sort of several viable alternative hypotheses. And I guess for me, and there I'm thinking, wow, how many countries have enough money and tech to do something like that, and they wouldn't tell you they were going to do it?
Right.
I guess at least dozens, probably not hundreds, but surely dozens. And I guess my cynicism is that I'm pretty sure that they wouldn't tell me they were going to do that, and I could easily imagine there being an unrecorded test of some sort by some other government. And
I mean, I learned through researching a little bit about this video that when the SR-71 Blackbird was being tested at the time back at Area 51, or Area 51, apparently the number of reported UFO sightings dramatically increased because people were seeing the plane reflect the sun as the sun was in the night sky. And so, I mean, it is obviously much more plausible that these videos and all of these things would just be from any other man-made creation. But I guess, do you expect that aliens are out there? Do you expect they would try to be contacting us? Do you think that we as humans should try to contact them? I know this is completely out of the realm of science, but
yeah. So first of all, I spent 5 years as a deputy principal investigator for a node of the NASA Astrobiology Institute, and I learned a ton about the biochemical origins of life in talking to biologists and people who study that. But the one thing I learned is that we have no viable theory for the biochemical origins of life. It is a miracle, a twin miracle. And I use that in the scientific sense of being able to have a membrane gather around genetic material that's capable of reproducing itself and a chemical engine that can extract energy from its environment, so-called metabolism. And there are many ways to do it. It's not beyond the realm of science, but we don't know exactly how it happened on Earth. We have a lot of theories about how it could happen. But I guess my feeling is that the emergence of life in the universe is probably very common. But if you talk to evolutionary biologists, they also diverge wildly on how likely it is that intelligence, such as we call ourselves intelligent, is a natural outcome of evolution, or whether the ants are going to be here when we're long gone. So if you ask me, like a Drake equation or a Fermi paradox, I don't think there is a Fermi paradox. I think we have absolutely no idea how likely it is that intelligent life could exist in the universe. And the universe is awfully big, and it lasts for a very long time. But I am not at all surprised we have not been contacted. I think the chances of us finding life elsewhere in the universe are very high. But I have absolutely zero idea whether intelligent life is common or rare. Zero. Right. And anything else is just me, what are the Minnesota Twins going to do 5 years from now? I don't know. You want me to talk about it? Sure. If I had nothing better to do, I'd talk about it. But given that I think I do, I kind of find it uninteresting to speculate. I even apply this to the sort of higher order terms in the Drake equation. How long do technological civilizations live? I don't know. I have no idea. I have absolutely no idea. So I tell people I'm absolutely convinced there's life elsewhere in the universe, and I have zero opinion on whether there's intelligent life elsewhere by many orders of magnitude.
Right. Like statistically speaking, like there's no way that given the observable universe that we're the only form of life, whether intelligent or not, let alone speculations that the actual universe is anywhere between 250 to 10 to the power of 53 times bigger than the universe that we can see. So I feel like, I'd have to agree that there's life there, but focuses should be not on whether or not it's intelligent, just how it evolves and how we can take away from that to improve what's going on here on Earth.
Finding life elsewhere, I think, well, number one, if I were starting over, I might get interested in biochemistry because I think it's just super fascinating. There are many different ways to construct a genetic code. There are many different ways. I mean, the origin of life is amazing, and there's a wonderful research going on in that right now. I think we don't know how to look for life. I don't think we will recognize it when we see it. I think looking for life in the universe right now is exploration. and that's a good thing to do with one's time. But to me right now, it's not quite yet science. And the reason I say that is what I came back to before. I think even harder than proving that you found life will be ruling out that there's life on something you looked at and didn't see anything that suggested life to you. Mm-hmm. So you're not going to know there's not life there. So what even is the experiment? Is it an upper limit? Is it a lower limit? What on earth am I doing? Right now, I'm just looking, and I'm going to try to see what's out there. But for me, that's not science. That's exploration, which is a great thing.
Mm-hmm.
Yeah, I think it's interesting how I would say for myself as well, when I was a kid, what first got me interested in astronomy wasn't the science. It was more the explorative side, or asking about alien life, watching science fiction movies, stuff like that. And it's interesting to see how, over the course of your career, over the course of education, it's changed. Where when you were a kid, you mentioned you were watching Cosmos, and at the end, Carl Sagan talks about alien life, talks about other worlds and how life may be different. But now you're, after kind of being exposed to the science and the rigorous hypothesis testing, you're saying it's not even a question that should be asked yet. It's still exploration. So I think that's
but finding life either elsewhere in the solar system that we could prove that was diverse from the one that started here, that's to me the science discovery of the century, because proving that it arose twice, that would fill me with such optimism. It can happen. It wasn't just a one-off. And if I find that on a nearby star, I mean, that's even better. It's just amazing. And so I guess while I'm not expecting to get up in the Millennium Falcon and, help defend it, I'm now even more excited about the prospect of just that philosophical question, that life has arisen independently multiple times. And frankly, we might even discover that on Earth. Maybe we're coexisting with biota we haven't recognized yet. Mm-hmm. Do we know how smart encephalopods are? I don't really think so, but I'm really thinking that we're underestimating most of the cognitive abilities of the species on this planet already. My dog is a lot smarter than I give her credit for, to be honest. So I think we still have a lot to learn about our own biosphere, in addition to trying to explore others. I'm all for that. Mm-hmm. I'm sorry to interject, but guys, I actually have to go. I have another meeting that I'm already late for.
We were going to thank you for coming on, and I think that was extremely interesting. We got to explore so many different topics with you and get your thoughts and ideas on a wide variety of things, both scientific and slightly less, borderline not at all scientific. But thank you very much for coming on to our podcast, and
thank you so much,
have a good
Professor
day.
Meyer.
Thank you so much. Take care, guys.